Okay, so wow, we have a full house today. We're thrilled. And I just mentioned to the students, Anna, that you're going to be our science teacher every Wednesday morning at 10:30
30, yeah.
Eastern, 9:30 Central. So we're really thrilled because it's great to know that we're going to have an interesting science class every Wednesday morning, something we can count on. So I'm really excited. This is our second session for Earth Week with Anna from the Michigan Science Center, and the one on Monday was unbelievable, like just an unbelievable session. So it was just can't say enough great things about it. So we'll do that one again because we can't post the recording for those of you who missed it. But for those of you who did see it, I bet you'll come back because I know that Kieran up in Iqaluit loved it. So we're going to turn it over today to Miss Anna, and she's going to talk about RAD reactions. So I see
Yes.
she's got some kitchen stuff there, and she's going to explain to us about some chemical reactions. So over to
Yeah,
you, Miss
absolutely. So
Anna.
thank you so much, everyone, for joining. If you are tuning in again because you've seen one of our programs, thank you so much. I'm so glad you're enjoying our programs and tuning back in. If this is the first time that we're meeting, my name is Anna, and I work at a place called the Michigan Science Center. We are pretty close neighbors, Canada and the States. So if you know where the Great Lakes are located, that's where the state of Michigan is, and that's where I live, and that's where the Michigan Science Center is. Now, we are talking about some chemical and physical reactions here during today's program. A lot of these reactions are things that you can try at home. But of course, I brought one that's a little bit more exciting, something that we can't necessarily try at home. But I'll give you instructions on how to do these, and then Molly and Katie, after the program, will also be able to send you the link to our website, which has guides to how you can recreate almost all these activities at home with instructions, with pictures. So if you have questions, I'm more than happy to answer them throughout the program. Just make sure that you're using the chat feature to communicate with me. Don't use the Q&A section because I can keep an eye on just one of those things. So if you have questions you'd like to ask me throughout the program, type them in the chat. But I also have a lot of questions to ask you to test your knowledge, to see what you already know about chemistry, and to kind of keep us moving along throughout the program together. It's going to be very, very fun. Now we're doing chemical and physical reactions, which are a part of chemistry today. So if we are talking about chemistry, and you've been here for one of our chemistry programs in the past, you know that we always talk about one thing first before we do any of our chemical reactions. Anyone remember, what do we always talk about first when we're doing chemistry? Dibbler told me. Anyone else have an idea? What should we talk about first always when we're trying to be good lab scientists? A couple more people telling me we should talk about safety first, always. So there are some safety precautions that we'll take throughout this program, especially with that one demonstration that you shouldn't try at home. But I said that most of these are safe experiments, so we don't need to worry too much. But if you remember, what are some important safety rules or safety equipment that I should have if we're working with chemistry? Tell me if you remember some of those items or some of those rules that we might have. A couple of them already, and I'm looking around for one piece of equipment that I know I just had a moment ago.
Alice says goggles. Gibbler says gloves. Alice said a coat. Yep.
There they are. All right.
I
So
see you have your hair tied
they
back.
disappear on me sometimes. I've got my goggles on, and I'll go ahead and keep those on throughout the program. People are telling me I've got my lab coat on. Absolutely. This is to protect my skin and my clothing from things that could either hurt me or just stain my clothes. That's not good. I do have a pair of gloves. I'll wear these only when we do our very last demonstration because that's the only one where I really, really need to make sure that this dangerous chemical doesn't get on my skin. So we'll go ahead and I'll put those back where just behind me for now, but keep in mind that I do have them. Now we're going to be working with a lot of foods today. So I've got a few different things that we might use either in cooking or in food. So for example, I've got some vegetable oil here. Do you remember a rule that we had when it came to food in the lab? I know we've talked about this one a couple times. If you've been here for our past programs. If you haven't been here, what do you think about food in the lab? Anything important we should maybe do or not do? Alice is pointing out my Beaker Woman dress. This is for our STEMinista project at the Michigan Science Center. So if you are a woman who is interested in science, technology, engineering, or math, you should check them out. It is the STEMinista project. We're trying to keep girls involved in STEM careers. Very, very cool. You can even get one of these shirts online too. No one chiming in about our food rule yet. Do you think it would be a good idea for me to eat anything that I'm using for science today? What do you think? Tell me in the chat. Good idea or bad idea? Yeah, I'm saying lots of no's, right? Absolutely not. So even though this really is vegetable oil that I got from the grocery store, we're not going to eat anything that we create here in our lab setting today. I'm also not going to bring anything into my table that is food. So maybe if I had some leftover breakfast, I'm going to keep that away because we don't want to contaminate anything. Everything on the table is now science equipment only, and so it's only going to be used for science. All right, so let's get started. Now that we've covered safety, I feel like we've covered our bases here and we have a good understanding of it. We'll be talking about chemical and physical reactions, and you might be curious as to why I've got some of my decorations here, because these really tie into a lot of our program today. We'll be talking about the difference between chemical and physical reactions, but for one of our experiments, we'll be talking about lava lamps. So decided to pull out some of my lava lamps here. Now, I actually collect lava lamps. Just fun fact about me, I have almost 30 of them. Most of them I get at garage sales. I think they are super, super cool because not only are they really fun to look at and kind of beautiful, they actually rely on a lot of science in order to function. So if we take a look at my lava lamps here, I've set up just 3 of them. I see some of you have lava lamps at home, which is great, which means you can set yours up after and think about some of these concepts that we've talked about. Now you'll notice that the lava lamps are moving, right? Maybe not the lamp itself, but the materials inside the glass. Now we're going to talk a little bit about how that process works today when we come to our chemical and physical changes. So in chemistry, Molly or Katie, will one of you switch me so that I can share my screen? We're going to talk about this process of what makes the insides of a lava lamp move. So we'll talk about chemical and physical reactions. There we go. There we go. All right. So we have 2 diagrams here. We have a physical change and we have a chemical change. Throughout the program, with every experiment that we do, I'll be asking you whether that was an example of a chemical or a physical change. So we need to understand what those 2 phrases mean first. So we have a physical change here on the left. These are water molecules, and they're going through a phase change. So on this side of the picture, on the left, we have liquid water. And if you look at those molecules, they're pretty closely packed together. Liquid water really likes to stick together and kind of flow, but we know it's a liquid. If we add heat to that reaction or to that liquid, right, those molecules will start to spread out. We go through a phase change and they turn into a gas. But take a close look at the molecules. Pick one water molecule on the left, think about it, and then look at one water molecule on the right. Do they look the same or do they look different? If you look at just one of them, do they look the same or do they look different? Tell me in the chat once you've made a decision. Those water molecules on the left look the same or different as the ones on the right. So don't think about, we're only picking one molecule for here, right? So pick just one water molecule, maybe this one right here. And then take a look at this water molecule right here. They do look very much the same. They're just farther apart. So we didn't change anything about the actual molecule in this change. All we did was add more energy, which spread those molecules out. So this is a physical change. We didn't create anything new. It's still water at the end. So we've got water on the left and water on the right. Now, if we take a look at the other side of the screen, right, it says that this is an example of a chemical change. This process is hydrogen peroxide turning into water. Now, they're drawn a bit differently, but you can see in this diagram that we've got 2 oxygens, which are blue, and 2 hydrogens, which are red when we're talking about hydrogen peroxide. 2 oxygen, 2 hydrogen. Over time, hydrogen peroxide will break down. It loses one of those blue oxygen molecules, and they look like this. It becomes water again with only 1 oxygen and 2 hydrogen. So these molecules look different as they go through a chemical change. We're actually breaking and making new bonds. So a physical change, right? We start and stop with the same materials, even though they might look different. We still have the same thing at the start and finish of our reaction. On the right, in a chemical change, right, we're creating something totally new. All right, so just keep those things in mind as we move through our reactions today. That way we can use that knowledge to determine what we're seeing, if it's a chemical or a physical change. The first reaction we're going to talk about has to do with how the lava inside this lava lamp moves around. Now, we say that this works based on a process called convection. As our molecules warm up, right, they start to rise. Just like in our diagram of water, those molecules get further apart, therefore less dense, and they start to float. But as they reach the top of the lava lamp, they then start to cool back down and become more dense than the water, and they sink down to the bottom. And you can see that this process happens continuously. As long as the lamp is on the bottom, heating up our wax inside the lava lamp, right, we can see that convection process taking place all the time. I've got to grab one material here. This material is in my fridge because I needed some very, very cold water. All right, so we've got cups here, or mason jars, full of hot and cold water. So right in front of me, I've got blue water, which is going to represent cold, just like we would see on the cold side of the sink. And then on this side, we've got red water, which is very, very warm. So again, just like you'd see on your bathtub or on your sink, blue means cold, red means warm. Keep that in mind. Now we're going to be stacking these beakers. Now, let's top these ones off a little bit more cold water. That way it's all the way full to the very, very brim. We're going to be stacking these jars and taking a look at what happens to our different colored water. This has to do with that same process of convection. So we'll start first by stacking the warm water on top of the blue water. So we'll make sure we keep these over the tray. This is, again, one of those experiments that you can try at home. All you'll need is 4 of the same size glasses. So I chose mason jars because I know they're all the exact same size. But if you have glasses at home, drinking glasses that are all the same size, you can use those as well. The important thing is that they're exactly the same size so that we can stack them without them falling off each other. Let's take a zoomed in look at our table here. We said that our first experiment will have us stack the warm water on top of the cold water. So we'll take our laminated card, which we've used in the past doing a similar experiment that we called gravity fail. Hold it over the tray because it could spill just a little. And we're actually just going to balance these 2 glasses right on top of each other. The important thing is that they're exactly lined up, so we'll bring our cup over to the edge, and I'm going to remove the card from between them. So keep them right on top of each other, being very, very careful here. What do you notice about our 2 colors of water? Are they mixing together or are they staying separate? Yeah, Gibbler tells me that for the most part, they're staying separate. Other than that very center spot where our colors are touching, right? Maybe there we see a little bit of mixture, maybe a little bit of purple liquid being created as we mix our red and blue. But for the most part, these two temperatures of liquid are staying separate. That's because warm molecules, right, will always rise. They always float to the top because they are much less dense, just like we saw in that diagram of the liquid versus gaseous water. Those molecules are spread further apart on top. They're less dense or lighter than the cold water on the bottom, and they'll stay this way until the room reaches, or until the water goes back to being about room temperature. Let's scoot that one over to the side. All right, now we've got one more experiment to set up. This time we'll set it up on the opposite way. So this time we'll put the red water, the red warm water on the bottom, and we'll put the blue water on the top. And while I set this up, tell me, what do you think is going to happen when I remove the card between our water this time? So use your what we've learned so far, use your prior knowledge about density, about temperature and molecules, and tell me what will happen when I remove the card this time. Remember that blue is cold and it's on top, and red is warm and it's on the bottom. Lots of great hypotheses here. Someone tells me they can bubble, that they might mix. Red will shift to the top. They're going to separate because they're different densities. Now remember, these were different densities as well, and they stayed separate. Chantel guesses that these will stay separate as well because they're different densities. All right, let's take a look. Oh man, look what happened almost immediately. You were right. Those liquids mixed together. That's because of convection. That process, that warm molecules will always rise to the top and cool molecules will always sink to the bottom. So since we set this up in the wrong direction, our blue molecules rush to the bottom, sink, because they're so dense. And our hot molecules rush to the top and floated up because they are so warm. So this brings us to our first question. Was this a chemical or a physical change? Tell me in the chat. You need to take a look at this diagram one more time. Put it up on the screen here. Tell me in the chat, was this a chemical or a physical change? We'll wait for a few people to answer here. Lots of great answers here. This was, in fact, a physical change. Now, even though we changed the color of the water when they mixed together, we didn't actually break or make any bonds. We still started and stopped with water. So this is an example of a physical change. Similarly, if you were to mix Kool-Aid powder into water, right? So maybe lemonade mix or Kool-Aid mix. If you were to stir that into water, is that a chemical or physical change? Think about that question. People telling me chemical, but let me ask you, when I mix lemonade powder into water, am I getting something that's not lemonade or water? No, right? It's still a physical change. All that is those lemonade molecules diffusing into the liquid. They're just spreading out to become even across the whole glass of water. And so that's still a physical change. Diffusion is physical change. It's still just water and lemonade powder. All right, now let's go back to our lava lamps here and talk a little bit more about them. So inside a lava lamp, you have both a liquid water and a wax. We say that wax is something that we call hydrophilic. hydrophobic. We might have talked about hydrophobic substances here on Echo Live in the past. Tell me, do you know what hydrophobic? No, type it in the chat. If not, let's break that word into two pieces. Hydro means water, and a phobia, if you're familiar with a phobia, say I had a phobia of heights or a phobia of spiders, right? It means that I'm afraid of something. So Isaiah and Charlotte told me that something that is hydrophobic won't mix with water. Gibbler tells me that it's scared of water. And those are both good definitions of what it means to be hydrophobic. So water is what we call polar. We look one more time at those molecules in our physical change diagram. We can see that there are two sides of a water molecule. One side that has the hydrogen atoms on it, that side is positive, and then the oxygen side is negative. So it works almost like a magnet. It has north and south poles, or positive and negative ends. Because of that, water really likes to be around other things that are polar, other things that will stick to it like a magnet. But waxes and oils are not polar. They're what we call nonpolar. They don't have a positive and negative end, which makes them afraid of water. They don't really like to be near each other. That's what keeps the wax from ever mixing into the liquid inside a lava lamp. So no matter how many times I turn on my lava lamps, no matter how many times this wax swirls around, once it cools back down, the wax will always separate. They'll never mix together into one big mixture. So that's talking about a hydrophobic and hydrophilic substance. If you're interested in creating your own lava lamp at home, one that doesn't run off electricity, it's very, very easy to do, and it only takes a couple household materials. So on this tray, I've got some vegetable oil, which is going to act as our hydrophobic substance. So oil and wax are both hydrophobic. I have an empty water bottle here that I've filled with just maybe 1/3 of the way with water. We'll just take off the lid here. Take off the lid and just a little. There we go. And I'm going to fill it almost the entire rest of the way with our vegetable oil here. We'll pour it in, and you'll notice that right now the oil and water are kind of mixing together. You might be able to see some droplets starting to form. But if we let it sit very, very still, you notice that those two substances separate back out. We're still left with the same amount of water on the bottom and oil on the top. That also has to do with density, right? So if we have oil on top and water on bottom, which one is more dense? Isaiah and Charlotte tell me it's like salad dressing. Yeah, absolutely. That's correct, right? So some salad dressing has a hydrophobic and a hydrophilic substance inside it, like oil and vinegar, that keep them separate. So before you use it, you always have to shake it up really well. But no matter how many times you shake it, right, they always separate back out. Think about this. We've got a couple answers coming in. Tell me, if the oil is on top and water's on bottom, which one is more dense? Yeah, we've got a lot of good answers. The water is more dense, right? So think about that. Things that are more dense have more molecules packed in the same amount of space, which make them heavier. So the water is much heavier than the oil, which is why it sinks down to the bottom. Now, to be able to see it a little bit better, let's add a couple drops of food coloring and watch what happens to the food coloring. What did we see happen there? One more drop, see if it starts to fall. Did the food coloring mix into the oil? Yeah, someone is telling me great scientific terminology here. It is high density, right? We saw it sink all the way through the oil, and it's not mixing with the oil. So if it's not mixing with the oil, do you think that makes the food coloring hydrophobic or hydrophilic? Remember that hydrophobic is afraid of water. Hydrophilic loves water. And I can type those words in the chat. Yeah, great answers here. Let me type that in the chat for you. Phobic, hydro. Yeah, awesome. So it must be hydrophilic. It must like water if it's not mixing in with the oil. So we'll just go ahead and we'll just gently shake that up. Let our oil and water mixture resettle here. And you'll see that the food coloring mixed into the water, but not into the oil. So it does need to settle just a little bit here. And just like our lava lamp, we can color the wax and the water differently. So in here, right, we've got clear water, but blue wax. Whereas in this one, we've got white wax, but pink water. And so we have to use different types of dye to accomplish that. We have to use types of hydrophobic dyes if we want to color the wax and not the water. All right, so let's come back to our DIY lava lamp here. We've got our wax or our oil in our water starting to separate. And so we see that we've got red water on the bottom and our kind of yellowy colored oil. Turn this into a lava lamp, right? We need something that's going to cause bubbles. So we'll use Alka-Seltzer, which we use a lot here on Echo. So if you've been present for some of our other programs, you might be familiar already with what happens to these Alka-Seltzer tablets when we drop them in water, right? We're familiar with the fact that when we drop them in the water, they start to fizz or to bubble up, right? So we'll go ahead and I'll break this in half. It's gonna pass right through our layer of oil until it gets down to the water because they're pretty dense and heavy. And let's take a look at what happens. We go. We're starting to see that lava lamp effect, right? Those bubbles are trapping that water mixture on the bottom, carrying it up through our oil. Once it gets to the top, right, those bubbles will pop, and then the water sinks back down to the bottom. Camera to focus a little better here. This is something super easy to try at home, right? It only took us 3 ingredients. We only need water, vegetable oil, and some Alka-Seltzer, which you can easily get at the grocery store or the pharmacy. They're very, very inexpensive, and they're great for lots of different experiments here. We said that this lava lamp works based on those principles of hydrophobic and hydrophilic substances. So phobic oil, philic water. And once the Alka-Seltzer runs out, you can actually let this settle and you can use it again. So it's not wasted. You can just cap your water bottle here. You can save it for later, and you can do that experiment again. All you need to do is drop in more Alka-Seltzer, right? That'll create those bubbles. They eventually run out and settle, and then you can save it to try it again later. Now, if we do want something hydrophobic to mix with something hydrophilic, we have to add what we call a surfactant. A surfactant is something that actually lets those two substances mix. It breaks down that polar barrier that keeps water so close together and keeps the oil away. Let's take a look at what a surfactant looks like if we were to see it as a molecule. So this is a surfactant molecule. An example of a surfactant is actually dish soap. Dish soap is a great surfactant. That's because the molecules have a water-soluble or hydrophilic head. So this green part of the molecule is hydrophilic. It loves water because it is polar. You can see that it has a positive and a negative end, just like water molecules do. So it can stick to them like a magnet. On the end, though, we've got a hydrophobic tail. A hydrophobic tail does not have positive and negative ends, and so it does not want to be near water. It wants to be near the oil. If we were to put these two things together, so if we were to put oil, water, and a surfactant all together, the surfactant molecules form these circles, which we call micelles. So they line up to form a barrier. And what they can do is they can actually trap tiny little droplets of oil inside these micelles and surround themselves with water, which makes it appear as if our water and oil are mixing together. So this brings us to this picture right here. And this is just a fun fact about how micelles work, especially when it comes to washing our hands. Right? So I know all of us have been told at some point in our life how important it is to use soap when we wash our hands. And that's absolutely correct. That's because there are oils on the surface of our hands. There's oils that our body produces, but there's also oils on the things that we touch all day. So if we use soap to wash our hands, we're actually able to grab on to some of those oils on the surface of our skin, and we can actually take them with us and wash them down the drain. If we only used water, right, this barrier would, or the barrier between the hydrophilic and hydrophobic substances wouldn't be broken. You need that surfactant in order to trap that grease or oil and carry it away down the drain. So it's really, really important. Actually, when we look at virus structures, so this is an example of a virus structure. Virus structures also are made out of oils. So if you use soap to wash your hands, these soap molecules can actually poke through that membrane, so break through that greasy membrane, break up the virus into tiny little unusable pieces that are now dead, and wash them down the sink. So washing your hands with soap is super important. C tells us in the chat that coronavirus does not like soap, and it's super true, right? You're exactly right that when these molecules break through the barrier on the outside of a virus, it kills them and destroys them. So that's why it's so important to use soap to wash your hands and not just hand sanitizer. Hand sanitizer is not a surfactant. I have an experiment to show you on how you can do an experiment about surfactants at home. We'll try this with, I have 2% milk in a dish here. So let me see if I can switch my camera over. Everyone still hear me here?
We can now, yeah.
Okay, perfect. I know that you said there sometimes you have to start and stop your microphone again, so perfect. All right, now this is 2% milk. If you have whole milk at home, it would work even better for this experiment. But we'll go ahead and I'm just going to add a couple drops of food coloring right to the surface of our milk. And you can see that they spread a tiny bit, but for the most part, our food coloring will stay kind of in its little droplet. That's because milk has fats in it, and fats are hydrophobic. They don't like water, and we know from our earlier test that food coloring is hydrophilic. It is made of water, and so it doesn't really want to mix with the milk. For the most part, it will stay together. Now, you may have seen this experiment online, but maybe not understood how it works. What we're going to do is I'm going to put just a small amount of dish soap right on the center of my finger, and I'm just going to drop it right in the center of our milk here, and watch what happens. our food coloring spreads out across the surface, right? Now we've broken that surface tension. We've interrupted the bonds that kept the hydrophobic and hydrophilic substances separate. So that surfactant, that dish soap, was able to kind of force these two substances to mix together. But think about this experiment, right? Look at our results, take a very close look. I have one more activity we'll try using the same principle, but tell me, is this a chemical or a physical change? Think about the picture of the micelles I showed you and look at our results to our experiment here. Is this a chemical or a physical change? Good answers coming in. This is still a physical change. So chemical reactions aren't the only ones that are exciting. This was still a physical change. Even though we broke up those oil or fat molecules into smaller bits while we trapped them in those micelles, those circles made out of surfactant, right? We still have oil and water separate. We've just broken them into smaller pieces. You can think about that like ripping a piece of paper in half. Even though we've made it smaller, it's still just paper. So this is still a physical change. We can see that physical change using water as well. So if you don't have milk that you want to sacrifice to that experiment, you can do something very similar using water and pepper. So all you need to do is sprinkle a layer of pepper across the surface of your water. The more you sprinkle on top, the better. And you can see that since these pepper molecules are really light, so not very dense, they actually stay on the surface of the water. Remember that water is polar. It sticks together like a magnet, and these pepper molecules are not. They are non-polar, and so they want to stay separate. So they're very light, and they're non-polar, so they stay floating on the surface of the water until we add this surfactant. So let's see what happens if we add just a drop of dish soap right to the very center. They spread to the edges and they actually start to sink down below the surface. So by doing that, you actually break the surface tension just like you would if you were washing your hands with soap, which breaks the surface tension of the water. All right, let me switch my camera back here and hit my microphone back up. So we've talked about surface tension. Now, when we dropped our Alka-Seltzer in the water for our lava lamp experiment, right, we still had a physical change. Everything stayed separate. You can see that it went right back to being oil and water. But this is kind of a tricky one because Alka-Seltzer it creates an acid-base reaction when you drop Alka-Seltzer inside water. If you were present on the day that we did pH testing, we tested the pH of a glass of water when we dropped some of this Alka-Seltzer inside. And we saw that when that happened, it actually acidified the water by creating that carbon dioxide gas. So we can do another experiment here. This one you can try at home if you have parent permission. Great question from Alice in the chat. She said, what is pH? The video is recorded. I think it was our kitchen chemistry episode. So if you'd like to go back and watch that episode, we talk a lot about pH, but pH measures whether something is an acid or a base. So acids are things like lemon juice or vinegar, or even battery acid is a really strong acid. Things like bases are actually things like dish soap, or drain cleaner, or bleach, or even baking soda. So acids are, she says her name is Anna too. Hello, Anna. Sorry, I don't mean to call you Alice then. So we have acids and bases, and Alka-Seltzer actually contains both. It has a little bit of citric acid, which we find in lemons, and a little bit of baking soda as well. When it's in its solid form, they don't mix together, but when you drop it in water, they start to dissolve and they start to make and change bonds, which means that when we do that, is that a chemical or a physical change? Think about what we just said. During an acid-base reaction, if we're making and breaking bonds, is that a chemical or a physical change? Lots of great answers coming in from Gibbler and from Maddie and from Elise. They all tell me that is a chemical change that time. So a chemical change, right? We're making and breaking bonds. Then we can actually use this for a different experiment that I think is super, super fun. So for this, you'll need a pitcher where we can combine baking soda and vinegar. And we've talked about baking soda and vinegar. It's kind of a classic science experiment. And when those two things mix together, vinegar is an acid and baking soda is a base. They start to bubble and fizz just like our Alka-Seltzer and create carbon dioxide gas. So we're going to do an experiment using our vinegar and baking soda. All you'll need is 1 cup of vinegar and about 2 tablespoons of baking soda. So we'll add both of those to our pitcher here. And they start to bubble and fizz. You can see it starting to happen in my pitcher there. But the point of this is not actually to look at this reaction. What we're doing is we're actually trying to trap those gases. That carbon dioxide is being trapped inside the pitcher because it is denser than air. So instead of floating away, the carbon dioxide is settling. It's sinking and it's staying inside this pitcher. Now I'm setting up on the table a row of tea candles. We said you can try this one at home, but of course, if we're working with fire or with candles, you need to have parent supervision to try this one. So while we let our carbon dioxide, that really, really dense gas, settle inside the pitcher, just lighting my row of candles here. We'll see if this one wants to light. Maybe not. There it goes. You can tell me in the chat while we're getting our candles lit here, is combustion or fire, is that a chemical or a physical reaction? Tell me in the chat, chemical or physical, a combustion reaction or fire? None of my candles are lighting here. Grab some new ones. Yeah, think about if we talked about the fire triangle, right? We talked about that it takes a source of fuel, heat, and oxygen in order to have a combustion reaction. And so you might know that that's a chemical reaction, right? When something is burning, when I burn things, like if I burn leaves outside, right? At the end, I don't have leaves anymore. I have something entirely new because I've broken bonds inside them and created something new. Move the ones that aren't cooperating for our experiment here. All right, so we've got our carbon dioxide gas, which is very, very dense and heavy, inside the pitcher. And what we're going to do is I'm just going to pour that gas over our candles here. I pick up our pitcher and I just gently start to pour the liquid, or not the liquid, just the gas. You can see that I actually created an invisible fire extinguisher. So because this carbon dioxide gas is so much heavier than air, take this one candle again, since it's so much heavier than air, it pushes all the other oxygen out of the way and it extinguishes the fire without even having to blow any air on it or use the liquid inside. So you can very easily recreate this experiment at home too. Remember, always get a parent to supervise you or help you out since we were working with fire in that experiment. All right. So in that reaction, right, we definitely saw a chemical change in our tea candles. We saw a chemical change inside our pitcher, which because we started with baking soda and vinegar, right? We started with baking soda and vinegar, but we ended with carbon dioxide gas. So that was an example of a chemical change or a chemical reaction. That Anna tells me pouring gas, she's never heard of it, right? But we can realistically pour anything that's heavy, right? We can normally think of pouring liquids because they're so much more dense than air that it's easy to do so. But we can pour gases as well, even if they are invisible and we can't see them. So this is a great time to take questions if you have them. I do have one more experiment to show you. That is an example. I won't tell you actually, but it is an example of one of these chemical or physical changes. So if you have questions that you'd like me to answer before we get to that last experiment about anything we've done so far, type them in the chat. We can answer a few now, and then we can always come back and answer a few more at the end of the program as well. So think about that. I'm going to get set up for our last experiment here while I wait and see if you have any questions about what we've done so far.
Well, C says you're the best, Anna.
Oh, thank you.
And Allison has to go. And Jack says Newton's 3 laws, every action has an equal and opposite reaction.
That's so true. Good science fact of the day. All right. Keep typing in your questions. We'll go ahead, and I know a few people have to sign off here, so I'll go ahead and we'll get to our last chemical reaction here, or chemical or physical reaction. And we'll tell you the ingredients. That way you can tell me at the end what we've made. Is it a chemical or a physical change? So this reaction is elephant toothpaste. And this is the one that I said I'll need to wear these protective gloves. So these gloves are here to keep my skin safe because the main ingredient in elephant toothpaste is highly, highly corrosive. It is hydrogen peroxide. So we've got hydrogen peroxide here inside this big white bottle, which does not look like the hydrogen peroxide we have inside our house. So this hydrogen peroxide is a lot stronger. The stuff that we put on our cuts and scrapes in order to clean them is about 2% hydrogen peroxide. And that stuff burns pretty badly when you get it on your skin. That's how we know it's doing its job. It's eating the organic matter like bacteria that can be inside our cuts and scrapes. But this stuff is about 35%. So more than 10 times stronger. And so it's very, very corrosive. If I were to get this on my skin, even when it's not inside a cut or scrape, it could burn me pretty badly. And so I'm wearing the gloves to keep my hands safe just in case anything were to splash. We'll just go ahead and pour some of our hydrogen peroxide down inside our Erlenmeyer flask. Now, if you think about the diagram we showed about chemical and physical changes, right? We said that hydrogen peroxide has the formula H2O2. So 2 hydrogen and 2 oxygen, which makes it really unstable. It does not like to be hydrogen peroxide. It really wants to be water, H2O. And that process is actually happening right now, which is why we normally keep hydrogen peroxide inside a solid colored bottle in order to keep the light out of the bottle and keep our hydrogen peroxide as hydrogen peroxide longer. All right, so first step of our reaction here is just adding some food coloring. So I'm adding food coloring a little bit down the side of the glass and a little bit to the bottom. Now tell me, did adding the food coloring, was that a chemical or a physical change? What do you think? Chemical or physical change adding food coloring? Yeah, a physical change, right? We definitely don't see anything happening inside the beaker. There's definitely no fizzing reaction like we saw with our acid-base reaction. And so all it's done is change the color of the liquid. It's still just hydrogen peroxide, and so that was a physical change. All right, let's add something else to the mix. Next important ingredient in elephant toothpaste is dish soap. We'll add a good amount of dish soap down there to the bottom of the flask and tell me, chemical or physical change? Close look if you need to, chemical or physical change? physical, right? Still nothing happening, nothing exciting at least happening inside the beaker. So adding dish soap, again, just a physical change. The dish soap is here to help trap the products of this reaction. So what we'll do very lastly is we're going to add some potassium iodide. Potassium iodide is a salt. It's a pretty powerful salt, and it's going to add to our reaction. And then you can tell me if this is a chemical or a physical change when we add potassium iodide. All right, here we go. 3, 2, 1. What do you think? Chemical or physical change? Good answers, everybody. My bubbles are getting away from me here. This is a chemical change. We can see that not only have we created a big pile of soapy bubbles, right? We're also, you might even be able to see some steam rising off of our reaction here. So this pile of soap bubbles is incredibly hot as well. So while we made and broke bonds, there was some energy left over from this reaction. So once our bonds were done breaking and reforming, we had leftover energy, which was released from this reaction in the form of heat. So you might not be able to see the steam rising off here. So I've got one trick I can show you. And if I take a reading of the temperature on these bubbles, and I'll zoom in here on my temperature gauge if I can find my remote. And you can see that this reaction is 157 degrees Fahrenheit. That's incredibly hot. Let me see if I can switch it here. Celsius. That's about, now that it's even cooled down just a little, it's about 68 degrees Celsius. So an incredibly hot chemical reaction that was created by that process of making and breaking bonds. This was our last reaction of the day. You can see that I've got a bit of cleanup here to do of my big soapy bubbles. But if you have any last questions before we sign off about our experiments or about chemical and physical changes, let me know in the chat, and I'll keep an eye out for those questions.
Okay, so Isaiah and Charlotte want to know, does vinegar and baking soda actually help clean the surface like soap and disinfectant?
Not on your, so it does not do anything in order to break up the hydrophobic or hydrophilic substances, right? So we dropped that Alka-Seltzer, which is an acid-base reaction, into our lava lamp. But did it force our oil and water to mix together? Did it keep them separate? Or I mean, did it form them into one mixture? No, right? So it's still oil and water. So acid-base reactions do not help us to wash our hands or to destroy any of those bacteria or virus cells. So that does not do anything for that. If you've heard about baking soda and vinegar being used for cleaning, that's a different principle. It's actually able to kind of break up stains on surfaces pretty well. So it is good for cleaning surfaces, but not for destroying living cells. So it's not good for killing bacteria. It's not good at killing viruses, and it's not designed to get grease off of your hands. Different principle, but it is good for cleaning substances in your house, like your laundry.
And oh, I had it here. Someone wanted to know, I'll find the name. What can you use instead of Alka-Seltzer? Because I know that that's not easy to get all the time, and we might not always have it in our kitchens.
That's a good question. So you need something that would fizz and bubble. I'm trying to think. Alternatives could be something like pop rocks, or if you were to choose to pour vinegar into the bottom of your bottle, you could try to drop in some of that baking soda instead. So if you have vinegar and baking soda in your house for cooking or baking, you could try that. Your results might look a little different, but the principle is the same. Vinegar is hydrophilic, just like water, so you could use vinegar instead of water, and then just sprinkle in your baking soda and see if that gets you the same results. If it works, take a video and send it to Molly and Katie on the Connected North at Home site, so they can show it to me. I'd really like to see it if you do try something else. So if you can think of something else to recreate your own lava lamp, show me.
That would be great. We'd love to see some videos because that would be just like awesome. Izzy's wondering if it's like the Mentos and Coke experiment, if it's sort of like that.
It's sort of like that. So if you remember to our Mentos and Coke reaction, we said that there's no chemical reaction happening there. That's also an example of a physical change. There's not actually any reaction taking place. What's happening when you drop the Mentos down inside the Coke is that the air bubbles actually trap on to all the tiny little microscopic bumps that are all over Mentos. We also did it with salt. Because it's very porous and very bumpy, it's actually able to grab onto those carbon dioxide molecules and let them out of the solution. So at the end, we haven't made anything new. That's still a physical change, but it just released the gas that was trapped inside the liquid.
That's awesome. And Isaiah says, when you add yeast to flour and water and sugar for bread, is that a chemical reaction?
Yes and no. So I'll answer that in two parts. If you were to mix them in a bowl, right, nothing really happens. But if you add heat to that reaction, so when you put that in the oven to try to bake bread or bake something like a cake, right, then we have chemical reactions or chemical changes happening. So sometimes just mixing together your ingredients isn't enough. Sometimes they need more energy in order to push that reaction to completion. So when we're baking, we actually need that heat. That heat will activate our reaction, just like in this case, just like our potassium iodide was the thing that we needed in order to push that reaction along. Because we said the peroxide was already starting to break down just because of the light inside this room. It happens very slowly. But when we add this catalyst, this potassium iodide, it makes it go much faster, just like baking something in the oven.
That's excellent. And the last question, because we know we have to go, Jack would like to know, how many years have you been a scientist?
Good question. That's kind of hard to answer. I guess it depends on when you say I started being a scientist. I would say that I started doing science when I was pretty young. Probably when I was 7 or 8, I started doing science experiments at home with my family and at school with my teachers. But then I loved it so much that I went to college and started studying science. And so I would say that it's been a few years, maybe like 8 years or so since I started officially being what people might consider a scientist. And I've been working at the Michigan Science Center for 5 years. So I've been doing science for education and for kids and families for 5 years.
That's amazing. And you're so good at it. And Kieran says that he loves science, and Jack says thanks, and Gibbler says thank you with about a bazillion exclamation marks. So I guess we'll see everyone hopefully later today for dance and drawing. And oops, I've got one more thing coming up today. The endangered animals. So we'll see you then. And next week, we'll see Anna on Wednesday at same time for the planetarium tour. That's going to be awesome. So thank you so much. This was so much fun.
Welcome. I'll see you all then.
You're welcome, everyone.
That was awesome. I love your sessions.
I love these. These are so great. Okay, thanks.